Good morning, good afternoon. My name is Marcos Lopez and today I'm here to present a study about the fuel cell stack sizing and the dynamic limitations effect on hydrogen consumption and durability of a fuel cell system operated for automotive applications. We are the CMT Motores Termicos, and we are, probably some of you know us because you have already worked with us. So we are a research institute that has been working in the automotive industry for more than 40 years with more than 100 active researchers. And in this case, during the last years, we have been focusing our research on hydrogen fuel cell technology because we really believe that it is a technology that is promising to decarbonize the transportation sector. Along this presentation, we will focus first on introducing the motivation of this study, describe the objectives, the methodology, then we will analyze the results of the study, and then we will jump to the conclusions. So why have we focused our research on hydrogen fuel cell? Well, in Europe especially, but also in the industry in general, we have seen recently quite a lot of interest on developing hydrogen fuel cell technology to decarbonize the transportation sector, and in particular for the light-duty vehicle application, durability, together with the limited number of hydrogen refueling stations are preventing the, let's say, the mass deployment of the fuel cell vehicles along the industry. So in light of these situations, what we did was propose a range extender fuel cell range extender vehicle. It's like a plug-in vehicle with a medium to high power fuel cell and a moderate battery capacity. And in this case, since you don't depend solely on the fuel cell and on the hydrogen, you can accelerate the fuel cell vehicle mass deployment, you can increase the fuel cell durability, and potentially reduce the total cost of ownership and the cradle-to-grave emissions. How do we solve this problem? How do we face this problem? Well, at CMT Motores Termicos, we researched fuel cell technology from the cell to the fuel cell vehicle level, both focusing on modeling and experimental activities. In the modeling side, we use GT Suite for 0D and 1D activities to model the fuel cell stack, fuel cell system, and fuel cell vehicle that we have used in this study, but we also use 3D CFD for the cell scale. Regarding the experimental activities, we have a test bench for fuel cell system of up to 200 kilowatts and a hydrogen production facility of high purity and high pressure to operate this testing facility. Furthermore, we have purchased recently a fuel cell vehicle, and we have a dynamometer where we are going to start soon the activities to do a technological assessment and, well, obtain data, state-of-the-art data about the fuel cell technology. However, before starting this study, we already did some studies. In this case, we started analyzing the cradle-to-grave emissions of the fuel cell vehicle technology with respect to the other technologies in the automotive industry, and we concluded that it is possible to actually decrease the cradle-to-grave emissions of all of the transport sector if we use the fuel cell technology. However, once we started with this, we couldn't stop, of course, and we started modeling activities to understand the impact of the fuel cell range extender architecture. So we developed these design spaces where you could obtain the hydrogen mass that you need in the tank, the hydrogen consumption, and the energy consumption with by selecting, well, a battery capacity, a fuel cell stack maximum power, and a target range for your vehicle. These design spaces were then converted to cradle-to-grave emissions, and that allowed to obtain the greenhouse gases and NOx emissions for different cycles of the life cycle of the vehicle as a function of the same parameters as in the previous study. So, as you know, as you have seen, we don't usually take a look at, let's say, only the performance part of the problem. We like to focus on other parts, the whole picture, such as, for example, cradle-to-grave, and in this case, this study, degradation. So the objectives of this study are basically to evaluate the hydrogen consumption and the durability under different conditions of fuel cell stack sizing and dynamic limitation. then understand how dynamic limitations affect the performance for different designs independently, and to elaborate design recommendations for the fuel cell range extender architecture to maximize the durability and minimize hydrogen consumption for the passenger cars. The methodology that we followed is to do a set of simulations, as you can see, with different fuel cell maximum power and dynamic limitations in terms of the variation of the current density rate variation with time. And what we knew at the very beginning was that increasing the number of cells of the fuel cell had an implication on the weight, but we didn't know what was the change, that potential change on the operation region for the fuel cell, and what was the effect on degradation. In fact, imposing dynamic limitations, we knew that, of course, it was going to have an implication on the energy management strategy, and of course an implication on consumption, but we didn't know how much degradation was decreased when imposing this dynamic limitation. What we really didn't know at the very beginning was, okay, we more or less can predict what is happening with the fuel cell stack sizing and dynamic limitations, but is there any cross effect between these two factors? Are the dynamic limitations equal for each design that we consider? So that's something that we answered in this study by using the GT Suite modeling platform, considering the fuel cell system models and the vehicle model. So for that purpose, as I've just said, we use GT Power and MATLAB. For the part where we use the GT Power, it was the powertrain modeling. So we validate and calibrate a fuel cell stack model. We designed the balance of plant. We optimize it and integrate it into a fuel cell vehicle. The second part was done with MATLAB, and this focused on optimizing the energy management strategy and developing a degradation model that was able to predict degradation during driving cycle conditions. So for the first part of the methodology, what we first did was to actually calibrate and validate a fuel cell stack model with GT Suite under different conditions of temperature and pressure, which is something that we actually expect in the let's say in driving cycle conditions. Then we build up all the models, auxiliary components that the fuel cell stack need to operate in driving cycle conditions. So we compose a fuel cell system and optimize it in such a way that we increase the overall fuel cell system efficiency over 60%. Finally, we integrated this fuel cell system into a vehicle architecture with a battery, a 30 kilowatt hour battery, and a 120 kilowatt electric motor. The second part was focused more on optimizing the energy management strategy. It was done with MATLAB and with the objective of minimizing hydrogen consumption under the constraint of charge sustaining. For that, we use the Pond-Triagin minimum principle, which basically says that if you find the minimum hydrogen consumption at each step of time, then you will find the overall minimum hydrogen consumption along your driving cycle. Then we developed the fuel cell degradation model, which is a model that we developed at CMT. And in this case, the basic philosophy of this model is, okay, we have reference degradation rates that we have developed, we have measured on let's say, laboratory conditions, and we are scaling these degradation rates based on two things. The first one is the electrochemical behavior of the fuel cell, that is, in this case, controlled by the voltage or the current density. And in the second part, the physical conditions under which the fuel cell stack is being operated under. So in this case is temperature and relative humidity, and we are scaling the degradation rate depending on the operating conditions, electrochemical and physical conditions of the fuel cell stack. We validated this model with driving cycle degradation data from the literature, and that's something that we have been using coupled with the energy management strategy in such a way that the two models are interconnected and they know what is doing the other model, so they can optimize each other. So the results, here we are going to see the results, and what we see is the current density evolution along the driving cycle for different designs and different dynamic limitations. So these two designs with different dynamic limitations are very dynamic in these two cases. And what we see is that when we decrease the number of cells, we are changing from the 100 kilowatt to the 40 kilowatt design, the current density increases. This is because if you have a lower number of cells to produce the same power, you will require higher current density. That's something that we notice here. And of course, if we increase the dynamic limitations, there are some peaks here that are not achievable because of the high dynamics. This has some implication in consumption because you are operating under suboptimum conditions, and this implies that the minimum current density here, in the case of the 40 kilowatt stack, increases to compensate for this suboptimum behavior. If we keep on increasing the dynamic limitations, we see here now how the models are lower dynamics, so the load change cycle intensity decreases. And this has some implications in the case of the highest restricted case, because if you limit a lot the dynamics of the fuel cell, what may happen is that the charge sustaining conditions may not be fulfilled during aggressive driving cycles. So the overall effects that we noticed when limiting the dynamics was that the minimum current density increased. In the case of 100 kilowatt, we can see it here when comparing these two simulations, because we need to compensate for this suboptimal behavior that we get when constraining even more the dynamics of the energy management strategy. The maximum current density decreases in overall, and the load change cycles, also the intensity and the number decrease. However, if we increase the fuel cell power, we get a decrease in the minimum current density, we get a decrease in the maximum current density, and the load change amplitude in the cycles is decreased, because actually, if you have a 100 fuel cell, changing the current density from 0.1 to 0.4 is not the same change in power as if you have a 40 kilowatt fuel cell stack and you change the current density from 0.1 to 0.3 to 0.4. In this case, what we realized also was that, okay, yes, we see all these effects, let's say, isolated, but when we take a look at the detail, we realize that everything that we have seen with respect to the effects of limiting the dynamics, these effects are also noticed in both designs, but they are let's say less intense. They are like dampened in the case of a 100 kilowatt design. So this means that higher power designs are less affected by these dynamic limitations, but they are affected. In the case of the dynamic limitations, what we see is that increasing the dynamic limitations decreases the degradation rate, so it is increasing the life, the durability, but it increases the hydrogen consumption, so the operation cost, due to the fact that, okay, yes, you are maximizing the life, but you are constraining the EMS, whose only objective is to minimize hydrogen consumption. So you are going to get some penalty on hydrogen consumption. And of course, there are no changes in production cost because the design is constant. If we take a look at how the degradation rate sources are evolving, in this case, what we realize is that in the very beginning, with almost no degradation, almost no limitation, the major source of degradation was load change degradation. But as you increase the dynamic limitation, it becomes a minor source of degradation, and other sources of degradation, such as start-stop and idle degradation, are more and more significant. And this is important because actually, if you are a fuel cell stack manufacturer and you know that your vehicle is going to have, your fuel cell stack is going to have some certain limitations because it's a fuel cell range extender, for example, then you will probably would like to focus on minimizing the degradation rate under high voltage or idle condition. So that's a way of applying this knowledge. In contrast, the effect of the fuel cell stack sizing effect on degradation performance is quite different. So we are perceiving that as we increase the fuel cell maximum power, we are decreasing the degradation rate and increasing durability, but we are also decreasing hydrogen consumption because we are decreasing the operating current density. So this means that the fuel cell system is operating under a higher fuel cell system efficiency. However, we didn't notice any let's say benefit in hydrogen consumption from the 80 kilowatt design. If we take a look at how the degradation rate source evolves with different design, at the 40 kilowatt design, the major degradation source is load change, but it is also the major source of degradation for the 100 kilowatt. However, it is significantly reduced because the load change cycle amplitude is also reduced. So in this case, we see that the effect of fuel cell stack sizing implies higher durability, lower hydrogen consumption, but higher operation cost. What we recommend here is that the vehicle manufacturer takes into account the let's say the durability that the manufacturer wants for their fuel cell stack. So according to that, he should calibrate the fuel cell stack size and also the dynamic limitations such a way that you have a similar durability than the expected durability, and not penalize, do not increase the dynamic limitations, because then you will get a penalty on hydrogen consumption. When we combine the effect of performance and durability, we see the same trends as we have just said, but the thing is that at very high dynamic limitation, 0.01 or 0.001, we actually see no benefit in changing the fuel cell stack sizing, because both the hydrogen consumption and the durability are quite similar. So in this case, we need to take into account that if we are a vehicle manufacturer and we are, for example, manufacturing a vehicle which is a conventional fuel cell vehicle, then the sizing is very important. But if you are thinking on a fuel cell range extender vehicle and you are going to have some limitations on the dynamic, then what happens is that maybe that sizing is not that important. So this is critical, and this needs to be taken into account in this case. So the conclusions here are basically that the dynamic limitations imply a higher durability, higher hydrogen consumption, and no change in production cost, while increasing the fuel cell stack power increase the durability, implies lower hydrogen consumption and increased production cost. But when we have very high dynamic limitations, the effect of the fuel cell stack sizing is not that relevant. However, what we suggest is a design with an 80 kilowatt fuel cell and a dynamic limitation that is, let's say, enough for the target life that the vehicle manufacturer wants for his fuel cell vehicle to maximize durability and minimize hydrogen consumption. So thank you everyone, and if you have any question, feel free to ask.